Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand firmament of scientific history, certain achievements shine with a unique and enduring brilliance, illuminating the very power of human intellect to comprehend the cosmos. Among these landmarks, Urbain Jean-Joseph Verrier's 1846 series of papers culminating in Sur la planète qui produit les anomalées observées dans le mouvement d'Uranus détermination de sa masse, the Sun orbit et de sa position actuelle, stands as a monument to the predictive capacity of mathematical physics. This work, born from meticulous calculation and unyielding confidence in gravitational theory, represents the apotheosis of the Newtonian worldview. It was an act of celestial mechanics, so profound that it famously led to the discovery of a new world, a planet found at the end of a pen before it was ever captured by the lens of a telescope. Verrier's analysis of the Uranian orbit was a supreme intellectual performance, a transformation of a troubling anomaly into a spectacular confirmation of cosmic order, and a demonstration that the universe, in its grandest motions, was indeed governed by noble, quantifiable laws. This achievement was a declaration that the reach of mathematics extended beyond the visible, capable of discerning physical truth from the faintest of orbital The intellectual stage for Verrier's work had been set over the preceding century and a half. The foundation was Sir Isaac Newton's law of universal gravitation, a principle of such elegance and power that it had successfully tamed the motions of the moon and planets, reducing the heavens to a system of differential equations. The subsequent mathematical architecture was erected by titans like Pierre-Simon Laplace, whose epic Traité de mécanique céleste sought to prove the long-term stability of the solar system, asserting that the mutual gravitational turns of the planets would result in periodic oscillations around a stable mean. This Newtonian and Laplacian universe was a clockwork mechanism of exquisite precision, yet a persistent and vexing flaw marred this perfect celestial timepiece. The planet Uranus, discovered by William Herschel in 1781, stubbornly refused to follow its prescribed path. By the early 1820s, the problem had become acute. The astronomer Alexis Bouvard, in constructing his authoritative tables of planetary motion in 1821, faced a confounding dilemma. He could fit the ancient, pre-discovery observations of Uranus to an orbit, or he could fit the modern observations since 1781, but he could accomplish both tasks with a single set of orbital parameters. The discrepancy was fundamental. Bouvard himself speculated that some unknown agent was acting upon the planet. As the years progressed, the deviation of Uranus from its predicted longitude grew ever larger, moving from a subtle concern for specialists to a glaring crisis for celestial mechanics. The very universality of Newton's law, the bedrock of physical science, appeared to be in question. The choice was stark: either the inverse square law of gravitation required modification at such vast distances, or an unseen body was pulling Uranus from its calculated course. It was into this intellectual crucible that Urbain Verrier stepped, at the behest of François Arago, the director of the Paris Observatory. Verrier, already a formidable figure in celestial mechanics for his work on the stability of the solar system, approached the Uranian problem with a characteristic blend of audacity and meticulous rigour. His initial papers on the subject, presented to the French Academy of Sciences in late 1845 and the summer of 1846, were masterpieces of methodical demolition and reconstruction. His first act was to perform a complete and exhaustive recalculation of the perturbations exerted on Uranus by its known giant neighbours, Jupiter and Saturn. This was a task of immense computational labour, requiring the evaluation of long, complex series expansions describing the gravitational interactions. In this process, Verrier uncovered and corrected significant errors in the foundational tables used by Bouvard, a testament to his exacting standards. Yet, even after this painstaking revision, a profound anomaly remained. The residuals, the differences between the newly refined theoretical position of Uranus and its observed position, were smaller, but they were systematic and undeniable. They constituted the pure, isolated signal of the unknown, the gravitational fingerprint of a hidden world. Verrier had cleared away the noise, leaving only the mystery itself, quantified and laid bare for theoretical thought. With the residuals precisely determined, Verrier embarked on the most challenging phase of his investigation, the inverse perturbation problem. The direct problem, calculating the gravitational effect of a known body on another, was standard, if laborious. The inverse problem, deducing the existence, mass, and orbit of an unknown body from its observed effects, was a challenge of a completely different order of magnitude. It required solving a system of highly complex, non-linear equations with a multitude of unknowns: the mass of the hypothetical planet, and the 5 key elements defining its elliptical orbit, namely the semi-major axis, the eccentricity, the longitude of the perihelion, the inclination, and the longitude of the ascending node to render the problem tractable. Verrier made several simplifying yet powerful assumptions. He presumed the unknown planet's orbit lay close to the plane of the ecliptic, an educated guess based on the general architecture of the solar system. This reduced the problem's dimensionality. For the planet's distance, he cautiously used a value suggested by the empirical pattern known as Bode's law, which posited a regular spacing of planetary orbits, while publicly maintaining a healthy skepticism of its physical basis. This gave him a starting point for the semi-major axis. The core of his analytical brilliance lay in how he structured the mathematics. He formulated a series of equations where the observed residuals in Uranus longitude at various times was set equal to theoretical expressions involving the unknown elements of the perturbing planet. These equations were a web of trigonometric functions, a formidable system to solve by hand. Verrier employed a method of successive approximations, a brute force numerical technique that required immense personal fortitude. He would postulate a set of orbital elements for his hypothetical planet, calculate the perturbations it would induce on Uranus, compare them to the observed residuals, and then systematically adjust the elements to minimize the difference. This iterative process, conducted over months with pen and paper, covering mountains of foolscap with intricate calculations, was a Herculean feat of mental stamina. Through this exhaustive process, he constrained the possible orbits, narrowing down the location of the perturbing body. In his final paper, presented on August 31, 1846, he confidently announced his result a precise prediction for the new planet's position on the celestial sphere, giving its heliocentric longitude and a surprisingly small estimate of its apparent disk size. He had, in effect, performed a mathematical triangulation, using the wobbles of one world to pinpoint the location of an. The denouement of this intellectual drama was as swift as it was spectacular, solidifying Verrier's name in the annals of science. Armed with a conviction bordering on certainty, Verrier dispatched a letter containing his predicted position to Johann Gottfried Galer at the Berlin Observatory. His choice of correspondent was deliberate and astute. He knew that the Berlin astronomers, under the direction of Johann Franz-Senke, possessed new, highly accurate star charts of the relevant region of Aquarius, charts unavailable in Paris. The letter arrived in Berlin on September 23, 1846. That very evening, Galer, assisted by his student Heinrich Louis d'Arrest, pointed the observatory's Fraunhofer refractor to the coordinates supplied by Verrier. Within an hour of starting the search, Galer exclaimed that he had located a star of the 8th magnitude that was absent from their new chart. Subsequent observation confirmed its planetary nature through its slight motion against the background stars. The new planet, later named Neptune, was found a mere 52 arc-minutes, less than 1 degree from Verrier's predicted position. The discovery was an immediate global sensation. It was a triumph of pure reason, a vindication of Newtonian physics that echoed far beyond the walls of observatories. The news demonstrated, with a clarity and force that the public could grasp, the astonishing power of mathematics to reveal the hidden structure of reality. This singular French triumph was soon complicated by a transatlantic echo. News from England revealed that a young, brilliant Cambridge mathematician, John Couch Adams, had independently performed similar calculations and arrived at a comparable prediction for the new planet's location nearly a year earlier. Adams had communicated his results to James Challies, director of the Cambridge Observatory, and to the Astronomer Royal, George Biddle Airy. The handling of Adams' work by the British scientific establishment provides a compelling study in contrast. While Verrier was public, assertive, and drove his research to a direct observational test, Adams' work circulated privately. Airy, burdened with administrative duties and possessing a sceptical disposition toward grand theoretical claims, failed to mount a dedicated search with the urgency the prediction warranted. Challies did begin a slow, methodical survey of the sky region, even recording the planet on 2 separate occasions before Galer's discovery, but failed to compare his observations and recognize its movement. The episode was less a failure of Adams' mathematics and more a complex interplay of personal temperaments and institutional inertia. The ensuing dispute became a matter of nationalistic pride, a scientific rivalry between France and Britain. Ultimately, the international community adopted a diplomatic and historically just resolution. Both Verrier and Adams are now credited as the co-discoverers of Neptune, their independent calculations standing as twin peaks of 19th century theoretical astronomy. The legacy of Verrier's 1846 work is profound and multifaceted. Its most immediate effect was to place Newtonian gravitation on an unshakable pedestal. For the next 7 decades, its authority was absolute, its predictive power seemingly boundless. The discovery of Neptune became the ultimate classroom example of the scientific method, an inspiration for generations of physicists and astronomers. Emboldened by this success, Verrier himself attempted to apply the same inverse perturbation method to another vexing celestial problem, the anomalous precession of the perihelion of Mercury's orbit. He hypothesized the existence of an intramercurial planet, which he named Vulcan, to account for the discrepancy. For decades, astronomers searched for this phantom world. The failure to find Vulcan is as instructive as the success in finding Neptune. The method was sound, but the underlying physical theory was incomplete. The Mercury anomaly was a whisper from a deeper reality, a puzzle that would find its resolution only in the curved spacetime of Albert Einstein's general theory of relativity. Furthermore, Verrier's triumph directly inspired the subsequent search for a trans-Neptunian planet. Percival Lowell's calculations of perturbations on Uranus and Neptune, while based on flawed data, set in motion the search at the Lowell Observatory that culminated in Clyde Tombaugh's discovery of Pluto in 1930. The quest for Neptune created a methodological paradigm that shaped planetary exploration for almost a century. In conclusion, Urbain Le Verrier's determination of the orbit of the planet Uranus and the subsequent prediction of Neptune's existence was far more than the discovery of a new celestial body. It was a defining moment for science, a point at which the abstract power of mathematical theory was shown to possess a tangible, predictive grip on the physical universe. The papers of 1846 represent a summit of computational and analytical achievement, a monument to human perseverance in the face of immense complexity. Le Verrier's work took the subtle, accumulated errors in the motion of a distant planet and forged them into an inescapable pointer, directing the telescope's gaze to a new member of the solar family. This achievement was the final, resounding chord of the Newtonian symphony, a perfect expression of the mechanical, deterministic universe that had dominated scientific thought for 2 centuries. It was a moment of supreme and beautiful certainty, occurring just on the horizon of a new era that would introduce the profound and unsettling complexities of relativity and quantum mechanics, forever changing our conception of the cosmic order.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.